All right. Now the last topic is going to be properties of solution. And these are very, these are real concrete properties that we see all the time, especially in the winter. So here they're putting in antifreeze into a radiator, car radiator. It'll do it, it'll lower the freezing point, keep the water in the radiator from freezing. And in the summer, it increases the boiling point, stops the water from boiling over. So we're going to review solutions a bit. So solutions are transparent, they don't separate on standing, they contain small particles, ions, and molecules that can't be filtered. They pass through semi-permeable membranes. They don't reflect light either, so we can't see the particles. Colloids, on the other hand, are very common. These have larger particles. They can't be filtered either, and they are separated by semi-permeable membranes. Now, colloid particles are large enough to reflect light. So if you shine light at a solution that contains a colloid, the solution will light up. You'll see the particles bounce off that. So you could say that the dust in the air is an example of a colloid, because when the sunlight hits streams in through a window and hits the air, you see the dust particles in the air, which you wouldn't see if the sunlight didn't hit them. So we're breathing in those dust particles all the time. So here are some vegetables that they're saying are really colloids. Let's check them out. So see how vegetables look like they're one thing, they're a mixture. Particles dissolved in it have a lot of water. Okay, now next we're going to look at is suspensions. Now suspensions are the largest particles of all, and they settle out because they're so heavy. You can filter a suspension easily, collect those particles. And suspensions have to be stirred usually to stay mixed. So we really don't like suspensions because we always have to stir them up. Think of like any kind of a bottle of a medicine you have that says shake before using. That's really a suspension. Here are some examples here: blood platelets, muddy water, calamine lotion. Okay. And so here is here's a chart from your book that compares all three of them, which is good to check out. So this is a slide that's also going to show you the same thing here. So different types of mixtures. So these are all mixtures now. So we have solutions, and it's showing you a little particle here that nice and stay suspended. Colloids also stay suspended, but maybe suspension particles get caught in the filter paper. And here we have a bag, a semi-permeable membrane, and you see in the bag we have solution, colloid, and suspension. And what happens? Only particles that can get out through the bag into the surrounding solution are these solution particles like ions and small little molecules in water, obviously. So here's a quiz for you. A mixture that has solute particles that do not settle out but are too large to pass through a semi-permeable membrane is called a, and what do you think the answer is? It's a colloid. Good. Let's check out some of these colligative properties. Now, colligative property actually means properties that depend on the number of solute particles in solution. So the more concentrated the solution, the greater effect that has on these colligative properties. And so for our solutions, we talk about freezing point lowering and boiling point raising or boiling point elevation. So, antifreeze could also be called anti-boil, and we leave it in the radiator all year long. We don't take it out. And the solute particles disrupt the formation of solid crystals, and that's how they can lower the freezing point of a solvent. Now, what about boiling? Well, for boiling, they also disrupt the boiling point, and so you have to have a higher and higher temperature to keep getting rid of these solvent particles. Here's a prime example. We see this in the wintertime. They spray salt and sand on the roads. Now, sand is not a solute because it doesn't dissolve. Sand, the properties of sand is that it's insoluble in water, and you can use that to grip the road. So you want sand on icy roads so you can grip it, but you throw the salts on the road so that you want the ice to melt. So here we use sodium chloride and we use calcium chloride. So the more ions you get from these solutes, the better it is at lowering the freezing point, which really means melting the ice. Now, the calcium chloride is used along with sodium chloride. You get 3 moles of ions in calcium chloride. Now, they don't use that much calcium chloride with it because of the cost. It's more expensive than sodium chloride. If you buy rock salt in a hardware store, you're really buying sodium chloride. You can buy calcium chloride, but they won't sell it by that. They give it a different name. Usually there's little pink pellets. Okay, now we're going to check out osmosis, which is the movement of water from a low solute concentration into a container of a higher solute concentration through a semi-permeable membrane. And if you look over here, the example they have is water on this side, semi-permeable membrane in the middle, and then a water solution, sucrose and water. Now the sucrose particles are too big to get through the membrane. So we actually have movement of water in both directions. But on this side, there's more water molecules lined up on the membrane than on this side, because on the solution side, some of this area is taken up by the sucrose molecules. So what's going to happen? So water is going to move into this solution, and as it does, its concentration will go down, and its volume will go up. Now, will it do it forever? No. What happens? Gravity is going to take over. Gravity is trying to pull the solution in the opposite direction. So we will have water going in here and becoming a more dilute solution. So the sugar can't get out of there. So the movement of water through a semi-permeable membrane is called osmosis. Water always flows into the higher concentrated solution. So osmotic pressure is produced by the solute particles in the solution. And this actually really means the pressure needed to reverse the osmosis. So if I want to push that water back where it came from, it would take some pressure. And so that's what we mean by osmotic pressure. The greater the number of dissolved particles in the solution, the greater the osmotic pressure. All right, let's check out a question then about this stuff. A semi-permeable membrane separates a 10% sugar solution from a 5% sugar solution if sucrose is a colloid. All right, so fill in the blanks. Solution A, or is it solution B, has a greater osmotic pressure? 2, water flows initially from which one? And 3, the level of solution of which one will be lower? All right. So the answers are, oops, I think I missed that. Here we go. Okay, now solution A has the greater osmotic pressure because you're saying from this 5% sucrose solution because it's dissolved in water. If the sucrose was a colloid, it wouldn't break up as much and it's not going to give you that same effect. Water initially flows from B into A, and the level of B will wind up being lower. Because for B, the sucrose isn't really dissolving. That's why that's happening. So B is more like just water. And that's why we get these answers. Okay. Osmotic pressure in blood. Red blood cells have cell walls that are semi-permeable membranes. They maintain an osmotic pressure that cannot change or damage occurs. Right? They must maintain an equal flow of water between the red blood cell and its surrounding environment. So we have 3 different types of solutions here. We have isotonic solutions. So here's an example. We see our red blood cells. Isotonic solution, a red blood cell retains its normal volume. Iso means equal. So an isotonic solution exerts the same osmotic pressure as the body fluids, such as red blood cells. So in other words, it's an equal movement of water in and out of the blood cell. So the blood cell itself doesn't really change. So 5% glucose solution or a 0.9% sodium chloride solution are typical isotonic solutions. And this is what they give to people in hospitals, or if they've had an injury, they lost a lot of blood. They give them these rather than just giving them water. Now a hypo means below or less. So let's see what happens in a hypotonic solution. You have a lower solute concentration in the red blood cells. So water flows into the cells by osmosis. The increase in fluid causes the cell to swell and burst. That's called hemolysis. So there's more, here we see the arrow, there's more water flow into the cell than out of it. So we're talking about in a hypotonic, a solution concentration that's less than what it should be. And then we have the opposite, which is going to be hypertonic, where you have a solution concentration that's greater. In this case, the cells are going to shrink, and that's called crenation. Water goes out of the cells by osmosis, and we get crenation. Both of these conditions, crenation or hemolysis, of course, are bad. Now, in dialysis, solvent and small solute particles pass through an artificial membrane. Large particles are retained inside. Waste particles such as urea from the blood are removed using hemodialysis, which is an artificial kidney. And you can see what's going on up here. Hemolysis, this is really a summary of what we went over before. You might know somebody that's undergoing dialysis, waiting to get a kidney. Okay, so indicate if each of the following solutions is isotonic, hypertonic, or hypotonic. So you have to remember to go back and review the slides here. So we have 2% sodium chloride, 1% glucose, 0.5% sodium chloride, or 5% glucose. And the answers are C, hypertonic. Because 2% is a lot. So you notice isotonic, the only one is A, a 5% glucose solution. And for sodium chloride, it's supposed to be 0.9%. 0.9% NaCl. So if you notice here, this solution is less than that. That's why it's hypotonic. And for the glucose is less than 5%, that's 1%. Sodium chloride is bigger than 0.9%, that's why it's hypertonic. Okay. When placed in each of the following, indicate a red blood cell will not change, undergo hemolysis, or undergo crenation. Again, you're comparing it to those standard concentration amounts in the blood. Okay, and the answers would be, number 1 is A, 5% is what we want, so nothing's going to happen. For B, 1% is obviously less, we're going to get hemolysis. Cells are going to blow up and burst. And then for B, you're going to have the same thing as too small. And then for C would be crenation, they're going to shrink. And here's a concept mass now of the whole chapter, which you might want to check out. It shows you everything that we covered. So we went from the beginning, what's a solute and a solvent? Took a look at solutes and solubility charts. We talked about saturated versus unsaturated. Then we looked at solutes as electrolytes. You can have strong and weak electrolytes. Strong, dissociate 100%, weak, dissociate just a little bit. Or non-electrolytes, which don't dissociate into ions at all. That was all in part 1. And then today we've looked at concentration in terms of percent and molarity, and dilution, so under concentration. Under molarity, we took a look at moles and volume more than anything. And then we ended with solute particles. We took a look at colloids and suspensions a little bit, not much with suspensions though. We looked at colligative properties, which are changes in boiling point and freezing point. And then we took a look at osmotic pressure. And that's it for the show.